Hello everyone. So in these lectures now we will go to interacting theory. Okay. So let me try to explain the phrase interacting theory and free theory a bit. So up to this point, we have considered theories whose exact spectrum is known. Okay. And such a theory we will refer as free theory. Very vaguely speaking, any quadratic theory is a free theory. Okay, this is a very vague definition because we'll try to make it precise later. So for the moment, just go ahead with this. And this means that what happens is that whenever there are non-quadratic terms, we cannot compute the exact spectrum. And as a result, we also cannot compute all the correlation functions exactly. Such a theory is called an interacting theory. Okay. So in general, any non-quadratic quadratic theory is interacting. Again, this is a vague definition. We will make it precise soon, but let's at least go ahead with this definition for next 2-3 lectures. So what will be a good example? So one example, in 0 plus 1 dimension, for example, consider half phi dot square minus half m square phi square minus lambda over factorial 4 phi to the power 4. Okay. So because of this presence of this term, we cannot find the spectrum exactly. Similarly, you can also consider analogous theory in 3 plus 1 dimension. where the Lagrangian density is okay. So in general there are many examples. Okay, so the question is that the purpose of this lecture is to find a method to compute time ordered correlation function in the of the Heisenberg picture operators. Okay, where this is the ground state or the vacuum of the full theory. And these are Heisenberg picture operators. Okay, so this is our purpose, and the way we will do it, we will use interaction picture to compute the above quantity perturbatively. We will explain it soon, that what this term means. Okay, so let's now move on to interaction picture. So in order to do that, let's consider the following thing. Let's say with the full Hamiltonian of the system, where H0 is free Hamiltonian, so what does it mean? It means that the exact spectrum is known. Okay, and this is usually called perturbation. And we assume lambda is small which means that take any state of the free theory, compute the expectation value of lambda, and then take the ratio with respect to the energy of the free Hamiltonian. This is much less than 1. Okay, where these are states of the Hamiltonian, states of H0, and this should be true for all n zeros. Okay, I mean, if it is satisfied for some of them but it is not true for other, then of course we cannot use perturbation theory. So this is our assumption. So in that case, what do we do? In that case, what we do is that in order to do that, let's first quickly review the 3 pictures of quantum mechanics. Okay, so we will of course elaborately discuss the 3rd picture, which is the interaction picture, but let's just quickly discuss the other 2 pictures. So when one is Schrödinger picture, in which states evolve but operators do not evolve in time. I forgot to mention one thing. So we also assume that H0, V and hence H do not depend on time. I mean, of course, there is a more general scenario when they depend on time, but for simplicity, we assume that they do not depend on time. Then in this case, the Schrödinger picture is this, that we evolve the states, but we do not evolve the operators. The Heisenberg picture the states don't evolve, but operators evolve in time. Okay, and then we come to interaction picture. Where a mixture of these things basically happen. So let's try to understand that. So in order to do interaction picture, first what we do, so let's first define the following things. Let's first define time evolution operator. So what are the time evolution? What is that? What does it mean? So time evolution operator means is that it's an operator. So this is an operator ut comma, let's say t0, such that I h bar del t of ut comma t0 is the Hamiltonian times ut comma t0. This is a full Hamiltonian. That means, so which this implies in Schrodinger picture any state at time t is essentially ut t comma t0 acting on a state at time t0. Whereas, so this is Schrodinger picture, whereas any operator at time t is same as the operator at time t0. Okay. This also means in the Hamiltonian, in the Heisenberg picture, the states as we discussed, it doesn't evolve, but operators in the Heisenberg picture, this will become u inverse t comma t0 operator at time t0 and then ut comma t0. Okay, so this is the utility of the time evolution, this time evolution operator. So now in order to define the Dirac picture or the interaction picture, first we define time evolution operator with respect to the free Hamiltonian. Okay, so what do we mean by that? So let's denote that. We mean that there is a operator which we denote by u subscript 0 t comma t0 is same as h0, the free Hamiltonian, times ut comma t0. Okay, so that's our first step. Then second thing is that, so first we define that. Second is that then we define interaction picture operator. Which is very similar to this expression with a slight difference. So the interaction picture operators is u0 t comma t0 o at time equal to t0 u0 t comma t0. Okay, so the only difference here is that here we used u0 rather than u. Okay, so I forgot to mention, we also assume that all pictures match at t equals to t0. Okay, so this is our assumption. So t0 is some arbitrary time, it doesn't matter what is that time. So if this is our definition of the interaction picture operator, so let's specialize to two particular operator. What about our free Hamiltonian? So this is u0 t comma t0 Hamiltonian, so at t0, and then u0 t comma t0. But h commutes with u0 because h is defined with respect to, so h commutes with u0, which means this thing just becomes u comma t0, and then we also assumed h also doesn't have any intrinsic time difference. So this is I forgot to mention h0. I'm sorry. Yeah. So this is the h0. So then basically that means that the free the free operator, the free Hamiltonian in the interaction picture do not at all evolve in time. But let's now try to consider the evolution of the interaction part. So this is same as u0 t minus t0. V was our interaction part, t minus t0. Okay, but note that V doesn't commute with H0. This implies that the interaction Hi of t is time dependent. Even if V is not. This is the artifact of the interaction picture. Because we are doing things in the interaction picture, that's why this is happening. Okay. Okay. Then in the interaction picture, the states evolve with respect to the interacting Hamiltonian Hi of t. Okay, so that's why it is different. This is somewhere in between of Schrodinger picture and Heisenberg picture, because in Heisenberg picture it would have evolved with respect to the full Hamiltonian, whereas in the Heisenberg picture it wouldn't have evolved at all. Whereas in the interaction picture it actually evolves, but it evolves with respect to just the interaction Hamiltonian part, not with respect to the free part. Okay, so in order to do that, we first define this. So for t greater than t0, let's try to compute the difference of ut comma t0, which is the full evolution operator, and the free evolution operator u0 t comma t0, and let's call that ui t comma t0. Okay, so just this difference we call this thing. Question is, what is the expression for ui t comma t0? Okay, so this is easy to do. So first thing you can show that this ui t comma t0 satisfies the following differential equation. Okay, so this is the differential it satisfies, you can show, and the solution to this differential equation is known as the Dyson series. Probably you have done it in your quantum mechanics course. Is known as the Dyson series. So let me try to explain the subtlety Dyson series. Let me try to explain the subtlety. The subtlety here is that the interaction Hamiltonian, since it is time dependent, then the interaction Hamiltonian at two different times do not commute. This implies that the ordinary expression that you would guess for this thing, something like exponential does not satisfy the differential equation. And the reason is this, that the interaction Hamiltonian at two different times do not commute. So the solution is essentially is known as the Dyson series, which has the following expression. The only difference between this expression and the above, the expression I am writing and the above expression is this operator T. So this is the operator, time ordering operator, which we introduced previously. And once you do this, you can show that this ui of t satisfies the correct differential equation. It basically what happens is that when I take derivative with respect to ui of t comma t0 I h bar, then this will bring down a factor of hi of t. Question is that in the absence of time ordering, I have to think about various ordering of this hi of t, where to put the hi of t. But since there is a time ordering and since t is the future most time, this is same as but since this is the future most thing, this is same as hi of t. Sorry, time ordering. Which is same as hi of t, hi of t ui t comma t0. Okay, so this is the main thing. But note that we have done this only for t greater than t0. Please see the note. There is an analogous way to do t less than t0. Okay. So I am not discussing it here because it's very similar. It's not same. It's very similar. And I have given the details in the notes. So I am not discussing here. But the second thing to note is that this ui t comma t0, the second argument, is t0. So we have to define ui, let's say ti, t1, t2, where the second argument is actually variable. Okay, so the way we do it is the following. So the way this is equal to ui t1 comma t0 ui inverse t2 comma t0 provided t1 is greater than t2. Okay, and analogously there are also subtleties when t1 t2 is one of them is less than 0, one of them less than t0, both of them less than t0. I discussed all the case in the note, so please go through that. But the bottom line is that you can, in all these cases, you can write down this expression of ui t1 comma t2 as time ordering exponential I h bar t2 to t1. So here t1 is greater than t2 to t1 hi of t dt. Okay, so this is the final expression of uit for all t1 greater than t2 greater than minus infinity less than plus infinity. Okay, and later in the next lecture we will see how we will use this expression to compute our original thing, that's the correlator in the interaction pictures. Okay.